In this example, we're going to be using the app again to look at the relationship between viscosity and flow rate. So we are told here at the beginning that we are to set the pressure, the radius, and the length constant. So I have the app, and I'm to set the pressure at 100, do the little slider, set the radius to 3, and set the length to 50. There we go. And we're looking at viscosity, so I'm going to change my graph to viscosity. And I see this downhill pattern in the graph. And then we're to record the viscosity for the different, or the flow rate for the different viscosities. So this first one is 63.6173, and then I would change my viscosity up to 3. There we go. And I see I get 21.2058, and I would continue. So I'm just going to write in those values. So right here, let's see, we had 63.6173, and then we had 21.2058. And I didn't show the rest on screen, but I did them ahead of time. So I had 12.7235, 9.0882, and finally 7.0686. So that's the data, and I definitely want to take time to look at what's going on in the data, but let me look at the questions, and then we'll come back and make some observations with the data. So we are told blood doping is the practice of injecting oxygenated blood into a person to enhance athletic performance. The emission of these red blood cells increases the viscosity of the athlete's blood. What is the impact on flow? So viscosity goes up. So I see that in the chart, 13579, an increase in viscosity. And I look at what happens to flow, and as I move down my chart, flow decreases. So this would actually serve to decrease blood flow. Next, I'm asked what is varying. So this is asking me what are my two variables. And so these are the two columns in my chart, viscosity and flow rate. My pen seems to be struggling, so we'll get there. Flow rate. And then it asked me what type of variation. So this really goes back to what I observed in question 1, and that is that I observed that as the viscosity values went up in value, the flow rate values went down in value. So one goes up and one goes down, which is an inverse relationship. Or we can use the wording indirect relationship. So we can say indirectly proportional, indirect variation, inversely proportional, all of those different phrases, but inverse is the key. We know that when we go to find an inverse equation, we want to use division. So these words direct us to use division. We have to know the order to put things in. And so when we put things in columns, the X column is first, the Y column is second, and we typically write equations Y equals. So I'm going to use, instead of Y, I'm going to use F for flow rate. I'm going to use V for viscosity, so I know what my variables mean. And I'm going to model this with the equation that the flow is inversely proportional, so that's the K divided by the viscosity. It says find the constant of variation. So in order to do that, I need to pick an ordered pair to put into this formula. I can pick any ordered pair from my chart of data, I'm going to pick the first one because typically the math is easier. So the flow rate is 636173. I don't know the constant, and the viscosity here is 1. So to get rid of the 1 in the denominator, I would multiply by 1 on both sides. And I told you, typically that gives us the easiest math. These cancel. And taking 1 times anything is that thing. So my constant is 63.6173. Now I can use that constant to answer additional questions as long as I use it with my formula. So it asks me to predict the flow rate when the viscosity is 8. So flow rate is going to be 63.6173. That's the constant, filling that in for K. Viscosity of 8, so I put the 8 in the denominator for that. And then I'm going to divide to get to my answer. So that's where I get 7.952 as my answer.